Hello everyone, welcome to Chemistry Academy. Today we are going to discuss the second part of boron family. So the first thing is boron, about boron. So we know that boron is a non-metal and it exists in solid state with icosahedron shape. So what is special about this icosahedral shape of B12? You can see here that this is icosahedral shape. Like in tetrahedron, why the name is tetrahedron? Because it has four faces. In octahedron, there are 8 faces. Same way in hexahedron, like regular hexahedron means a cube, which has 6 faces. So icosa in Greek means it has 20 faces. So you can see these faces. These faces are triangular faces. So 5 faces are there, 5 triangles are there at the top, and 5 will be there at the bottom. And there are total 10 triangles in between, right? So you can see here that if this is a triangle, right, from these 5 angles, these 5 spheres, there is formation of 5 triangles up and 5 triangles down. Same way you can see here that from these 2 spheres, there is a formation of 2 triangles. One is downward and one is upward. So we can say at the top there are 5, in between there are 10, and at the bottom there are 5. So total 20 faces are there. Icosahedron means 20 triangular, equilateral triangular faces will be there. So there are 20 faces and these are equilateral triangles. The faces meet at 12 corners. So these corners are boron atom. That's why it is known as B12. Each boron atom is attached with 5 other boron atoms. So you can see here that each boron atoms is attached with 5 boron atoms, and that is not possible by a normal covalent bond because boron has only 3 electrons. So this is possible due to formation of 3-centered 2-electron bond. Boron always form covalent bond. We have studied that because of very high ionization energy of boron. Boron never exists in ionic form. It always form covalent bonds. Boron has highest melting point in its 13th group. Yes, it is around 2000. Boron has highest and gallium has minimum melting point. Boron has highest ionization energy. Yes, we have studied that. In order to remember the order of ionization enthalpy, if we make a W where each corner is representing one atom of that group, and if we pull the right hand side group by a small quantity downwards, then we'll get that the boron has highest and thallium is the second number, and we can find out what is the exact order. So yes, boron has highest ionization enthalpy in its group because of its small size. Boron has the highest electron negativity in its group. So this is about boron. Boron exists in two forms, amorphous boron and crystalline boron. So in order to prepare amorphous boron, it is also known as Moissan boron. It is obtained by reducing B2O3 with magnesium or B2O3 with sodium at higher temperature, and it is black in color. So the whole thing is that in nature, the ores of boron exist in the form of borax, or it is exist in the form of kernite. So what is happening that from nature, this is borax, and when borax is treated with acid, so if I explain this whole method, borax is a solid. When added to water, it will dissolve in water. Then it will react with water. So there is hydrolysis of this borax. On hydrolysis, there is formation of, or sodium borate, we can say, better is sodium borate. So on dissolving in water, it will react with water to form 2 tetrahedral units and 2 triangular units. So this is sodium borate and this is boric acid. So it is a buffer solution because boric acid is there, acid and its conjugate base is there. So now this whole system is treated with HCl. When we are adding with acid, strong acid H2SO4 or HCl, then what is happening that it is a salt of strong base and weak acid. When reacted with a strong acid will displace weak acid. So on reaction with this, there is formation of NaCl, boric acid and water. So now this is the final solution. The solubility of boric acid in water varies with temperature. If you decrease the temperature, boric acid is very less soluble. If you increase the temperature, solubility of boric acid is more because of the crystalline structure of boric acid. It has hydrogen bond. We are going to discuss about that. So what will happen that we can crystallize this boric acid from this solution by decreasing the temperature by a little amount. This boric acid will form crystals and we will separate boric acid from this solution. So what we have done here that this borax is treated with acid and there is formation of boric acid. The whole process I have explained. Now this boric acid is heated. On heating this boric acid, there is formation of B2O3, that is boron sesqui oxide. So there is removal of water molecule, dehydration of boric acid will form this. And now this B2O3 is treated with magnesium. So it is a redox reaction. Boron will reduce and magnesium will oxidize, or in place of sodium, this reaction can take place. So this is explained here. Boric acid on heating will form B2O3 solid and water vapors will remove. And this B2O3 when treated with magnesium, it will form boron and magnesium oxide. So this boron is known as amorphous boron. So formation of amorphous boron, generally this reaction is there, but we can say that this whole process is involved. First we'll treat the borax with acid, strong acid, then boric acid will crystallize. Then that boric acid is heated, strongly heated, then B2O3 will form, and then B2O3 is reduced to form amorphous boron. Method of preparation of crystalline boron. There are many methods to form crystalline boron. One of the method is by reducing BCl3 with hydrogen. Hydrogen is reducing agent. So here boron is present in +3 oxidation state. With the help of hydrogen, it is going to 0 oxidation state. So boron chloride is heated with hydrogen in presence of tungsten. It is acting like a catalyst and very high temperature is required to form boron in crystalline form, and HCl gas will evaporate it. Now same thermal decomposition of diborane, B2H6 on heating, strongly heating, boron will left and hydrogen gas will be liberated. So this is crystalline boron. And the third method is Van Arkel method, where Bi3 is heated. Again, boron will be left and iodine will be liberated. Properties or reactions of boron. So reactions of amorphous boron. Amorphous boron is more reactive than crystalline boron. So that's why we are doing reaction of amorphous boron. So very simple. The first reaction is reaction with oxygen. It will form its oxide, that is boron sesqui oxide, B2O3. This reaction will take place at high temperature because boron, either it is amorphous or crystalline, it has boron-boron bond, which is a covalent bond, right? So reactivity will take place at higher temperature. So boron react with nitrogen. Again, very high temperature is required to form boron nitride. We are going to discuss about boron nitride. There are two types of boron nitride. One of the boron nitride has graphite-like structure, while the other has diamond type of structure. Boron will react with halogen. Almost all halogens will react with boron, like fluorine, chlorine, bromine, and iodine to form boron halide. So this is also a reaction taking place at higher temperature. Boron, when heated with ammonia gas, there is formation of boron nitride and hydrogen gas will be liberated. Boron, when fused, means very high temperature is required because boron is needed in molten state and the melting point of boron is near about 2000 degrees Celsius. So boron, when fused with alkali, hydrogen gas is liberated and there is formation of Na3BO3. So these are the methods by which we can prepare boron, and these are the reactions of boron, and maximum reactions of boron is with amorphous boron. It is easy to react. Uses of boron. It is used to make control rods for nuclear reactors because we have to control the nuclear reaction. There is a control rod which will absorb the neutrons. So boron has a very high cross section for capturing of neutrons, and those neutrons emitted in nuclear reactor is slow neutrons or thermal neutrons, we can say. So it is used to make impact resistance, is still used in bulletproof jackets in the form of B4C or B12C3. So here again B12C3, between boron and carbon there is a covalent bond, and we know that B12 structure boron has covalent bond. So this is a type of covalent carbide. Like aluminium carbide, when we are saying that is ionic carbide, but boron carbide, boron always forms covalent bond. So this is a covalent carbide. Boron is a fairly rare element. It occurs as concentrate deposit in the form of borax and kernite. Both are chemically same. Only the difference is water of crystallization. In case of borax, the water of crystallization is 8, while in case of kernite, the water of crystallization is 2. So we can write boron in this form, but we are going to discuss that how to write this formula. So we are writing borax as Na2B4O7.10H2O and kernite as Na2B4O7.4H2O. So we are going to discuss about the structure of kernite and borax in a very logical form, which is difficult to forget, right? Electrode potential. So here we are discussing about trivalent reduction potential and monovalent reduction potential of the elements of this group, and boron does not exist in ionic form because of very high ionization enthalpy. That's why boron +3 and boron +1 reduction values are not given, but other like aluminium, gallium, indium and thallium are metals, so their reduction potential for trivalent metal and monovalent metals are given. So we have to learn that what is the meaning of positive and negative values of these potentials. Like here, the reduction potential of aluminium +3 ion is negative. It means that aluminium +3 ion do not want to reduce, it want to exist in +3 oxidation state. So from here, we can say that it suggests that aluminium has high tendency to form aluminium +3 ion, because reduction potential is negative, means oxidation potential will be positive. So aluminium want to exist in +3 oxidation state. Same way here from the table, this is thallium, and we know that thallium shows inert pair effect. We can see here that the reduction potential of thallium +3 ion is positive. It means that thallium +3 is unstable in aqueous medium, or we can say that it is a very powerful oxidizing agent in aqueous medium. Thallium +3 is very powerful oxidizing agent. The positive value of thallium +1, reduction potential of thallium +1 is negative, right? The reduction potential of thallium +1 is negative, and this value is easy to remember. We also know that the copper 2 + 2 copper, the value is plus 0.34 volt. Here it is minus 0.3 volt, but the magnitude is common in both copper and this thallium. So thallium +1 do not want to reduce. So we can say that thallium +1 is stable in aqueous medium. Same way we can discuss about aluminium +1 to aluminium, where the reduction potential is plus 0.55 volt. Here aluminium is unstable in aqueous medium and it is an oxidizing agent in aqueous medium, but it is a better reducing agent than oxidizing agent in aqueous medium. So here the positive value of reduction potential is telling that aluminium can easily be reduced to aluminium metal. Aluminium +1 can be reduced to aluminium metal. But if you see, this is Latimer diagram. From this data I have taken the value of aluminium to aluminium +1, which is equal to minus 0.55 volt. From this data we can say this is reduction, so oxidation potential will be reverse of that. We have to calculate from aluminium +1 to aluminium +3. We already know that from aluminium to aluminium +3 this value is plus 1.66. So using this Latimer diagram, we have calculated that what is the oxidation potential of aluminium +1 to +3, that is 2.76. So aluminium +1 is very good reducing agent in aqueous medium. It will convert into aluminium +3. So that is written here that it is a better reducing agent than oxidizing agent in aqueous medium. So this data is very important in mains and advanced. They are going to discuss the inert pair effect in terms of reduction potential. So two things are very important, that aluminium +3 is stable, aluminium +1 is unstable, thallium +1 is stable, thallium +3 is unstable in aqueous medium. Structures of important compounds of boron. So the first structure is BCl3. We know that BCl3 has trigonal planar structure. From hybridization we can calculate that. So we can find out here that there is no dimerization, though it is a Lewis acid, its octet is not complete, but B2ClC6 does not exist. Like BF3 is also a Lewis acid, right? And the dimerization of BF3 does not take place because there is a back bonding. And back bonding is maximum in case of BF3. In case of B2Cl6, back bonding is there, but it is less effective with respect to BF3 because there the back bonding exists between 2p pi and 2p pi. Here, the back bonding is existing between 2p pi and 3p pi, which is because of difference in the size of atomic orbitals, p atomic orbitals. The overlapping is not that effective, right? But it is sufficient that BCl3 does not exist in the form of dimer. So the other compounds of this BCl3, boron and chlorine exist, that one of the compound is B2Cl4. So this compound in solid state has this type of structure, and in gas phase it has this type of structure. So if you know the structure in solid state, we can say that we can find out that how many boron atoms are, what is the maximum number of atoms that can exist in the same plane. So if I draw a plane, because since this will be sp2 hybridized, so it should be planar, and this is also sp2 hybridized, so this should be planar. So I can draw a plane which will pass through these two atoms and all these four atoms. So maximum number of atoms in a plane in this solid state structure should be 6. While in gas phase structure, where we can draw a plane which is passing through these two atoms and these two atoms, right? A plane passing from these four atoms, one plane is possible, right? This plane. Or I can make a plane which is perpendicular to this plane passing through this atom, and these two atoms. So maximum atoms in a plane here is 4, while in this case the maximum number of atoms in a plane is equal to 6. So that this is not that important because not given in NCERT, but this is very important. BCl3 does not go dimerization because of back bonding. We have studied that as we move down the group, the back bonding decreases and the Lewis acid behavior increases down the group. BF3 has the lowest and BI3 has the highest Lewis acid character. The second molecule is diboron. We are going to discuss the properties of diboron also, but here we are studying only the structure regarding diboron. So we know that one BH3 molecule and the other BH3 molecule will dimerize to form this B2H6, and this is 3-center 2-electron bond or banana bond. So what is happening here, that boron has 3 electrons in the outermost valence electrons, right? Valence shell. So here there are 2 electrons are participating in normal covalent bond with hydrogen atom, and this boron atom, this electron is from this boron atom. This hydrogen atom has this electron. There are 3 nuclei, this boron, and this hydrogen atom. So 3 centered, but electrons are only 2. So these 2 electrons are shared between 3 centers, 3 nuclei. That's why it is known as 3-center 2-electron bond. Similarly, here this electron is for this boron atom, and these are 2 normal covalent bonds. This hydrogen has this electron, right? So these 2 electrons are shared between this and this atom. So again, it is forming a banana bond. This boron is sp3 hybridized. So we have to discuss that which type of atomic orbitals of boron is participating in hybridization. So let us discuss. Boron in ground state has this electronic configuration. Boron has 5 electrons in the outermost orbit. So if I write that what is electronic configuration, that is equal to 1s2, 2s2 and 2p1. So in ground state, there is only 1 unpaired electron. So in first excited state, there will be 3 unpaired electron. Now, since it is sp3 hybridized, so you can see here that 1 2s atomic orbital and 3 2p atomic orbitals will combine to form 4 sp3 hybridized orbitals. So the atomic orbitals which are participating in intermixing to form the hybrid orbitals, 1 is vacant and 3 have half filled, right? So there is formation of 4 hybrid orbitals in which 3 are filled and 1 is vacant. So when we are discussing the banana bond among 2 boron atoms, one boron atom has a vacant sp3 hybrid orbitals, while the other boron atoms has half-filled sp3 hybridized orbital participating. So what we are discussing here, that in this banana bond, if this electron is of this boron, right? So we are talking about hybrid orbitals. So one electron, this electron, because there are total 3 unpaired electrons. So these 2 electrons are participating in bond with hydrogen atom, right? So this is these 2 electrons. The third electron here is again participating in 3-centered 2 electron bond, but this atomic molecule, this hybrid orbital is vacant, which is forming a bond with this 3-centered 2 electron bond. Banana bond is there. So here we are mentioning that in the overall molecule, if you see, this boron has one vacant hybrid sp3 hybrid orbitals. This boron has also one vacant hybrid orbital sp3 hybrid orbital. So in overall molecules, there are 2 vacant sp3 hybridized orbitals of boron atoms. So maximum number of atoms in a plane, if you see here, it is sp3 hybridized. So this is the actual structure. So these 3 atoms are in the same plane, these 3 atoms are in the same plane, and this hydrogen is above this plane, right? Above and below the plane. So maximum number of atoms in a plane is equal to 6. In case of boron dihydride, B2H6, maximum number of atoms in a plane is equal to 6. And this is some information about the angle, that this is the terminal angle, and this is the terminal bond length between boron and hydrogen. And this is the bridge bond length between boron and hydrogen. So this bond length is bigger than this bond length, right? This is 119 and this is 133, I think in picometer this value is given. Among these 2 bond angles, this angle is more and this angle is less. So this is the data we should remember if we are able to, because this bond length will be more and this bond length is small with respect to that, and this angle is less and this angle will be more. So this is about diborane. We are going to study diborane in detail in coming lectures. Now the next is borax. We have to study the structure of borax. So chemically borax, we write Na2B4O7.10H2, but this writing is just to confuse you. There is no 10 water of crystallization. So what is the actual structure? So this is the actual structure where the water of crystallization is equal to 8, and it's very simple to draw the actual structure. So if I divide this, there are 2 Na plus ions. So we can say that if 2 positive charges there should be 2 negative charge over here. So you can see that 4 boron atoms are there. 4 boron atoms are there, and between 2 boron there is a BOB bond. So 4 BOB bond, right? And this boron atom or this any 2, either I will take these 2 or I will take these 2, there is another BOB bond. So 5 BOB bonds are there. Now you can see here that this boron atom is only making 3 bonds, right? So its hybridization will be sp2. So this is a triangular unit. This is a triangular unit, but this boron atom is making 4 bonds. So it is a tetrahedral unit. So in case of borax, the anion has 2 tetrahedral units and 2 triangular units. So when we add this borax in water, there are 5 BOB bonds. So when this anion will interact with water, react with water, which is known as hydrolysis, 5 water molecules will react or required to break this BOB bonds, and they will convert into 2 triangular units of boric acid and 2 tetrahedral units of BOH4 minus, right? So it has 2 triangular units and 2 tetrahedral units, and it's very simple. Make 4 boron atoms, attach 1 OH group with each boron atoms. Then these boron atoms are joined with BOB bond. Since there are 2 negative, means boron will take 1 electron, it will behave like carbon. So this is behaving like carbon and they can make 4 electrons. So BOB. So BOB bond is 5. So 5 water molecules will be required. BOH groups, we can see here that units, BOH units will be 4, right? So on hydrolysis, 2 triangular units and 2 tetrahedral units is going to form, right? So this is about borax. Another ore of boron is kernite, which is chemically Na2B4O7.4H2O. Similar structure here also. It has only 2 water of crystallization. So what they can ask, that what is the number of water of crystallization, they can give the formula of this kernite and borax, which is also given in NCERT. And it's very simple. If 4 boron atoms are there, symmetrically place 4 boron atoms, and we have to put one OH group with each boron atom, right? So that's why 4 OH group is there, and there is BOB bond, right? And here there is 2 positive, so 2 boron atoms should be in negative charge, with negative charge, right? So here 1 BOB, so 5 BOB. Again, water molecules required for hydrolysis will be 5 water molecule, and on hydrolysis, after hydrolysis, there is formation of 2 molecules of boric acid, and there is formation of 2 ions, BOH4 minus ions will be there. So this solution will behave like a buffer solution. Here also this solution will behave like a buffer solution. So if this formula is given, if you don't know that what is the water of crystallization, logically you can say there are 4 boron atoms, so each boron has 1 OH group. So 4 hydrogen atoms will be consumed there, right? So from there you can remove that 4 hydrogen atom. If you remove, so water of crystallization will be 8. Here also you can see the same thing. What we are doing, that BOH 4 OH group, so 4 hydrogen atom, if you remove from this, the whole hydrogen atoms are 8. If you remove 4, 4 will be left. So by that you can make 2 water of crystallization, right? So very logical. If you go through once, you have no chance to forget that what is the number of water. If you forget, remember this BOH and you can find out what is the water of crystallization. The next molecule is boric acid, and boric acid in solid form exists in this layered structure or planar structure, right? And this is crystalline structure of boric acid, and because of hydrogen bond, it exists in the form of solid or crystal. Now you can see that this is one boric acid molecule, and within this molecule you can see that one boric acid molecule is involved in 6 hydrogen bond. These bonds, dotted bonds, are hydrogen bonds, right? So one molecule is making 6 hydrogen bonds. You can see here that one molecule is attached with 3 molecules. How? You can see here that this is the molecule. Now I am counting that with how many molecules it is going to attach. So there must be one molecule over here, and this is the other boric acid molecule, right? This is another boric acid molecule, or we can say that these two is one boric acid molecule, right? And these two will be one boric acid molecule, and these two will be one boric acid molecule. So one boric acid molecule is surrounded by 3 boric acid molecule through 6 hydrogen bonds. Now about this oxygen atom is making 3 bonds. 2 are normal covalent bonds and 1 is hydrogen bond, or we can say that one oxygen atom is attached with 2 hydrogen atom, one through normal covalent bond, other through hydrogen bond, right? One hydrogen atom is attached with 2 oxygen atom, one through normal bond and other through hydrogen bond. So these are the informations which they can ask from the structure of boric acid. So one molecule of boric acid is attached with 3 other molecules of boric acid through hydrogen bonding. One molecule of boric acid is involved in 6 hydrogen bonds. Between 2 molecules, there are 2 hydrogen bonds. You can see here that this is one molecule of boric acid and this is another molecule of boric acid, and there are 2 hydrogen bonds. So between 2 molecules, there are 2 hydrogen bonds. Boric acid possesses a layer structure. The diagram shows part of one layer in which boric acid molecules are hydrogen bonded together. The bonds within each molecule are highlighted in bold, and the hydrogen bonds are shown by hashed lines. The hydrogen bond are asymmetrical with OH longer than OH. Yes, that is understood. So now moving to the next structure or next molecule, that is known as borazine. Borazine, also known as inorganic benzene, right? Inorganic benzene is C6H6. In place of 6 carbon atom, there are 3 nitrogen and 3 boron atom. So this is the actual structure. This boron is acting like carbon, and this nitrogen is also acting like carbon. Because it has lost 1 electron, it has gained 1 electron. Only difference is that in case of benzene, these are carbon atoms, so polarity is not there like this, plus and minus was not there, right? So this is more polar, means this is relatively reactive than benzene. This is also existing in liquid state like benzene, and it is an aromatic compound like benzene, and it has resonance like benzene. It has 2 structures shown here, right? So this is about borazine, B3N3H6, which is also known as inorganic benzene. So therefore, the borazine molecule is considered to be aromatic. Borazine has many properties that are similar to that of benzene. Both are liquids, both are aromatic, although it is more reactive as a result of the BN bonds, which are polar in nature, being somewhat polar than the purely covalent bond. The next structure is boron nitride, BN. बोरोन नाइट्राइड का पहला पॉइंट तो ये है कि ये कैसा सॉलिड है. बोरोन नाइट्राइड जो है वो कोवलेंट सॉलिड है, मॉलिक्यूलर सॉलिड है, आयनिक सॉलिड है. So this is a covalent solid. From structure we are understanding that it is a covalent solid. So boron nitride exists in two forms. One is known as graphite type of structure and the other is known as diamond type of structure. So this is layered form of boron nitride or hexagonal form of boron nitride, or we can say that graphite like structure of boron nitride. So this atom is nitrogen atom and this is boron atom. Now I can see here that this nitrogen atom is attached with 3 boron atoms, right? Or this boron atoms is attached with 3 nitrogen atoms. Okay, so this is the thing we can see here that like in graphite the 1 carbon atom is attached with 3 carbon atom. Here boron atom, 1 boron atom is attached with 3 nitrogen atom, or 1 nitrogen atom is attached with 3 boron atoms, right? Like this is happening here. So this is the structure. This is one layer and this is the other layer. Unlike in graphite where 1 carbon atom is there, polarity is not there in graphite, but here boron and nitrogen there is electronegativity difference. Because of that there is partial charge on these atoms. So the van der Waals force of attraction between one layer and the other layer will be slightly more than that of graphite. Like graphite, it can used as a lubricant, but graphite is a better lubricant than boron nitride. So in this layered structure, in boron nitride, the van der Waals forces holding the sheet in line with each other are stronger. So boron nitrogen is not a good lubricant as graphite. However, the use of boron nitride as a high temperature lubricant is because of its chemical stability. So it is chemically stable, so it can act like a lubricant at higher temperature. So this is very interesting. It has graphite type of structure, and you can see that how to decide that the crystal is covalent crystal or the crystal is molecular crystal. So this is, I'm writing formula Bn. So between one Bn and other Bn, what type of bond is there? There is covalent bond. So I will say that this is a covalent crystal. Like graphite, it is also a covalent crystal having high melting point. Now this is another form of boron which has zinc blende type of structure or diamond type of structure. What is zinc blende type of or diamond type of structures? Atoms are present at the FCC lattice point and half of the tetrahedral void is occupied. Similarly, here they are saying that it is FCC with respect to boron atoms, right? So boron atoms per unit cell is equal to 4 and half of the tetrahedral void is occupied by the nitrogen atoms. So it can have diamond type of structure, and you know that diamond has very high hardness, so abrasive nature. Here they have shown that this is for diamond and this is for boron nitride, and this is not the layered form of boron nitride. We are discussing this cubic form of boron nitride. So the hardness you can see here, this is known as corundum and this is known as carborundum. This is tungsten carbide. This is bulletproof jackets we are using, boron carbide, covalent carbide. This is boron nitride and this is diamond, right? So boron nitride is a covalent solid like graphite and diamond. Now this structure is not mentioned in NCERT, but in NCERT in a table they have discussed that covalent or network solid where they have discussed aluminium nitride, because most of the students will confuse aluminium is a metal and nitrogen is a non-metal. So most of them can write that this is ionic solid, but it is not an ionic solid, it is a covalent solid and this is the structure. Aluminium nitride is a covalent solid given in solid state NCERT and it has woodsite type of structure. What is the first line of woodsite which we should know? It is FCC with respect to anion and cation is present in tetrahedral void and half of the tetrahedral void is occupied. So here aluminium is shown here as a bigger metal atoms, right? and this is nitrogen atom. So it is HCP with respect to nitrogen atom, and half of the tetrahedral void is occupied by the aluminium atoms, right? So again, this you can see here that between aluminium and nitrogen, what is the bond? The bond is covalent bond. So it is a covalent solid. So I think that this point is very important with respect to IIT JEE. The next compound is sodium perborate. Formula is Na2B2O2 whole twice OH4.6H2. It has 6 water of crystallization, and you can see the structure. There are 2 tetrahedral units. There is no triangular units, right? And this is perborate. This peroxide bond is there. So what will happen that this compound we are using in our daily life, sodium perborate, is used as a bleach in laundry powders, automatic dishwashers powders, and whitening toothpaste. Although the formula is often written in this form, which is confusing because half of it is written. If I multiply this whole thing by 2, then Na2B2O6.8H2O will be there. But the water of crystallization, you can see that 2 boron atoms are there, and here boron has minus charge. So 2 OH group are attached to that. So from there we can find out that water of crystallization is equal to 6. So what will happen that at higher temperature, this bond will break. So it will produce peroxide ion, which will act like a bleach. So the compound is preferred to hydrogen peroxide because hydrogen peroxide in aqueous medium is unstable, right? So in many applications it is used because it is more stable. At higher temperature only this bond is going to break, right? So this structure is also very important, sodium perborate, right? So these are the things. And the last, I think this is the last structure. Yes, last structure is colemanite. When we study the preparation of borax, then this colemanite is going to come. So when we are discussing this colemanite, it is Ca2B6O11.5H2O. Again, they will ask that what is the water of crystallization. If you have the common sense about this type of structure about boron, then you can easily find out what is water of crystallization. Like here, 4 positive charges there. It means 4 boron atoms have negative sign, right? 1 negative. So they are acting like carbon. So here you can see that what I have done, I have made the structure BOB. There are 6 boron atoms. So 6 BOB is there. Then I have to put 4 negative boron atoms. So what I have done, I make 2 boron atoms with BOB bond right here. So these 2 and these 2 boron atoms I have made with, these are negative sign, right? So very simple to make that. There are 6 boron atoms, so 6 OH group will be there. So 6 hydrogen atom, if you eliminate from here, how many left? 4 left. So how many water of molecules will be there? There are 2 water of molecules. So if this is given and they are asking, no need to remember, by logic also you can find out that the water of crystallization is 2 here. When we do hydrolysis, we count how many BOB bonds are there. So 6 तो इसमें हो गए और ये 2 हैं, 8 BOB bonds are there. So when this anion will hydrolyze, 8 water molecules is required, and due to hydrolysis there is formation of 2 triangular units. यहाँ ये वाली जो है वो triangular units होंगी और जो negative वाले हैं वो tetrahedral units होंगी. So 4 tetrahedral units and 2 triangular units are there in this colemanite. There are 4 tetrahedral units, there are 2 triangular units, there are 8 BOB bonds. During hydrolysis, 8 water molecules are required. Resulting solution will act like a buffer solution. Why buffer? Because it is a mixture of boric acid, 2 molecules of boric acid and 4 molecules of its salt with a strong base. So it is an acidic buffer. There are 2 water of crystallization. So all the things are very logically you can do it. So let us solve whatever we have studied today. The number of vacant hybrid orbitals which participate in the formation of 3-centered 2-electron bond in diborane. So what we have discussed about diborane is B2H6, right? And we know the structure of diborane. So if I am drawing the structure of diborane, this is 2 normal boron hydrogen bonds. Then there are 2 3-centered 2-electron bonds or banana bonds. Then again 2 normal hydrogen bonds are there. So here if I am saying that boron has 3 electrons, so these are the 3 electrons of boron. And this boron has 3 electrons. So these are the 3 electrons of boron. And there is a bridge bonding here with hydrogen atom. So 3 centered and 2 electrons. So this is 3 centered, 2 electron. About this boron, when I write the electronic configuration in ground state, that is 1s2, 2s2 and 2p1. There is only one unpaired electron, but we know that the number of unpaired electrons should be more than 1, because normal bonds you can see that single bonds is equal to 2. So in ground state, this is electronic configuration. In first excited state, it will form 1s2, 2s1 and 2p2. So this is the excited state of boron, where in the outermost orbit, this 2s has 1 electron, 2p has 2 electrons, and there is one vacant 2p orbital. So these 4 atomic orbitals will combine to form 4 sp3 hybridized orbitals, and in these hybridized orbitals 3 electrons are there, so one hybridized orbitals will be vacant. So in this banana bond, one boron atom has half-filled sp3 hybridized orbital, while the other boron atom has vacant. So overall, if you see in this complete molecule, there are 2 vacant sp3 hybridized orbitals which is participating in bonding. So this line is given in NCERT, very important for JEE Mains and Advanced. Amorphous boron is produced by heating B2O3 with, we have discussed that borax is the ore. Borax is treated with a strong acid. Then boric acid will form. That boric acid is heated, then water will vaporize, then this anhydride will left. Now this anhydride is reacted with strong metals, right? So magnesium or sodium metals, in presence of sodium metals, when we heat, then there is formation of boron and metal oxide. So this is C option will be the correct. Orthoboric acid contains, so boric acid is also known as orthoboric acid. I think that this ortho word is used for boric acid, S3BO3. So for this boric acid, this is also known as orthoboric acid, because there is also metaboric acid, right? If you remove a water molecule from this, the polymer will form. So one water molecule, if I remove, I can write that this is HBO2 n times or x times. This is known as metaboric acid. So the acid which can have metaboric acid have the name with ortho also. So the water molecule will distinguish between these type of acid, ortho and metaboric. Like if we are saying that there is phosphoric acid, S3PO4. Phosphoric acid is also known as orthophosphoric acid. So if I remove a water molecule, I can form a series of whose formula is equal to HPO3 n times or x times. So this is known as metaphosphoric acid. Metaphosphoric acid. So here the question is that if we are saying orthoboric acid, boric acid and orthoboric acids are same. If I draw the structure of boric acid, this is the structure of, it exists in layer form, but I am just drawing the structure of one molecule of boric acid in which the boron is sp2 hybridized. So this unit is a triangular unit. This is a triangular unit, right? So BO3 3 minus units exist. Triangular, right? Here BO3 3 minus is there, but its shape is not pyramidal. It is trigonal planar shape. So D option is correct. A boron carbide rod is used in a nuclear reactor because boron, which is isotope, one particular isotope of boron is B10, has a very, so in nuclear reactor, in order to decrease the speed of nuclear reaction, we are using this because it has a very high absorption capacity. So that capacity is because it has high area of cross section for capturing neutrons. So in this nuclear reaction, that neutron is bombarded, not the proton. So these options are wrong, and it should be not having low, it has high area of cross section. So B option is correct. Which of the following statement is correct for lubricant boron nitride? So we have discussed that there are two type of boron nitride. One has graphite type of structure and the other has diamond. But diamond was acting like abrasive, like diamond is hard, so boron nitride Having a diamond type of a structure is hard, but lubricant is the layered structure, right? So if we go through the option white solid with diamond-like structure, diamond-like structure will not act like a lubricant. Slippery white solid with a layered structure similar to that of graphite, that is correct, and this is a lubricant at higher temperature because it is relatively less quality lubricant than graphite at room temperature, but higher temperature it is stable, so it is used as a lubricant at higher temperature. And there is a strong van der Waals force of attraction due to difference of electronegativity of boron and nitrogen, while in case of graphite there is no such polarity, all atoms are carbon atoms, so van der Waals forces between the planes are little bit high in this. Covalent liquid and is structurally similar to that of carbon monoxide. It is not a liquid, it is a solid. Soft, low melting point. No, it is a covalent solid. It can't have low melting point. So this is also wrong. Which of the following is an example of covalent carbide? So aluminium carbide is an ionic carbide because it is made up of aluminium plus 3 ion and C3 4 minus ion. So this is an ionic carbide. Similarly, when we are discussing about this beryllium carbide, beryllium 2 plus 2 times, and this is C4 minus. Again, this will form methane, right? On hydrolysis, this will form methane. Here, calcium carbide is there. It is also ionic carbide, calcium 2 plus ion and C2 2 minus ion. On hydrolysis, it will form acetylene gas, C2H2 gas will form. But this boron always form covalent bond, and this is B12 C3, and it is used in bulletproof jackets, so it is a covalent carbide. So why, if we don't remember, if we also remember the point that boron always form covalent bond, then we'll say that this is covalent carbide. Next question, which of the following is are correct about boric acid crystal? So what we learn about boric acid crystal, we can write here that one molecule of boric acid. So if this is boron, then these oxygen atoms should be at 120-degree trigonal planar structure, symmetry hona chahiye. So this is the structure of this one molecule. Now this one molecule, ye jo oxygen hai, it is involved in hydrogen bonding. This hydrogen is involved in hydrogen bonding. This oxygen is involved in hydrogen bonding. This hydrogen is involved in hydrogen bonding. This oxygen is involved in hydrogen bonding, right? So if you see, this hydrogen is also involved in hydrogen bonding. So one molecule is making 6 hydrogen bonds, and between two molecules, there is 2 hydrogen bond. One oxygen atom is attached with 2 hydrogen atoms and 1 boron atom, means it is attached with 3 bonds, 2 normal covalent bonds and 1 is hydrogen bond. And 1 hydrogen atom is attached with 2 oxygen atom, one through normal bond, other through hydrogen bond. So let us go now through the question. In its layer structure, 1 boron atom is attached with 3 oxygen atom, correct? 1 boron atom is attached with 3 oxygen atom. In its layer structure, 1 oxygen atom is attached with 3 atoms, 1 through hydrogen bond. So 1 oxygen atom is attached with 3 atoms, 1 through hydrogen bond and 2 through covalent bond. This seems to be correct. The B option is correct. C option, in its layered structure, 1 oxygen atom is attached with 5 atoms, 2 hydrogen atom and 1 boron atom and 2 oxygen atom. That is wrong. 1 oxygen atom is attached with only 3, in which 2 are hydrogen and 1 is boron. So C option is wrong. D option, in its layered structure, 1 boric acid molecule is attached with 3 other boric acid molecules. Yes, 1 boric acid molecule is attached with 3 boric acid molecules, right? Because here between 2 molecules there are 2 hydrogen bond. Between these 2 molecules there are 2 hydrogen bond. Between these 2 molecules there are 2 hydrogen bond. तो इस molecule से 3 boric acid के molecule attach हैं. We can go through the actual structure also. We can see here that we have discussed that this boric acid molecule is attached with 1 molecule here, 1 molecule here, and 1 molecule will be here. So 1 molecule attached with 3 molecules, and between 2 molecules there are 2 hydrogen bonds, right? So this option seems to be correct. So the answer of this question is A, B, and D. Moving to the next question, which of the following is correct for colemanite? So what we are saying that if we apply some logic, like if I'm putting some logic in front of you, which will help you to remember it, I can write that this is 2 times of calcium 2 plus, means there should be 4 boron atoms with 1 negative charge, right? So symmetrically there are 6 boron atoms. So we can place those boron atoms by making a benzene, right? We know that there are 6 carbon atoms in benzene. So symmetrically, if I want to place it, this is 6 boron atoms. Between these boron atoms, there are BOB bond and angle is 120 degree, right? Keeping that in mind, I am making these bonds angular. So this is BOB bonds, BOB bonds, BOB bonds. And there are 4 boron atoms which are negatively charged. So I can put this negative and I will connect them with BOB bond. Any two, right? Opposite, I can draw this BOB bond. Here negative, here negative. Now, each boron atom is attached with one OH group. Each boron atom is attached with one OH group. Each boron atom is attached with OH group. There are 6 boron atoms, so 6 OH group means 6 हाइड्रोजन एटम यहाँ कंज्यूम हो गए. टोटल हाइड्रोजन एटम कितने 10 है. इसका मतलब हो गया वाटर ऑफ क्रिस्टलाइजेशन कितना होगा 2 होगा. So now if we go through this, it has 5 water of crystallization. That is wrong. It has 2 water of crystallization. It has 2 water of crystallization. That is correct. It has 4 tetrahedral unit. That is also correct. And 2 triangular units. Its solution will act like a buffer solution. Yes, when we add this into water, how many water molecules are going to react? So first, when I will dissolve it, let me write here that I can write this whole thing as, so now I am writing here that this Ca2 B6, and you can count BOB bond, right? So BOB bond 6 and 2 8, right? So I am writing B6O8 here logically, and OH 6 because each boron atom has OH group. So now I can write that this is equal to 2 times of water of crystallization. So when I am adding this solid into water, this water of crystallization will dissolve in that, right? So there is formation of Ca2 2 times plus this anion, which having this anion we are discussing, and this anion has 8 BOB bonds. So 8 water molecules. Now this I'm discussing about hydrolysis of this. So 8 water molecules will be required. Due to reaction with water, what is going to happen that the boron which do not have any charge is converted into boric acid. So there is formation of 2 molecules of boric acid. And there is formation of 4 units of BOH4 minus. This is tetrahedral units and this is triangular units. So this solution will act like a buffer solution. This is a buffer solution. So this seems to be correct because this is boric acid and it's salt with a strong base. If I write what is pH, pH is equal to pKa plus log. In the denominator, it should be boric acid. So 2 molecules of boric acid and its conjugate base will be 4. So pH की value अगर हम calculate करें तो that is equal to pKa plus log 2. If we know what is the pKa for boric acid, we can also calculate what is the pH of this colemanite buffer solution. It is an acidic buffer or mixed buffer. Next question, for crystal form of boric acid, find the value of x plus y plus z where. तो हमें कितना याद है, हमें क्या करना है, एक बोरिक एसिड का मॉलिक्यूल बनाना है एंड ट्रायगोनल प्लेनर. सो वी नो दैट कि कैसे बनाना चाहिए हमें 120 डिग्री पे. नाउ विल पुट OH ग्रुप हियर. ये हो गया बोरिक एसिड मॉलिक्यूल. नाउ कीपिंग इन माइंड दैट ये वाला ऑक्सीजन एक हाइड्रोजन बॉन्ड बना रहा होगा, ये वाला हाइड्रोजन भी हाइड्रोजन बॉन्ड बना रहा होगा, ये वाला हाइड्रोजन बॉन्ड बनाएगा, ये वाला ऑक्सीजन अगेन हाइड्रोजन बॉन्ड फॉर्मेशन करेगा, ये हाइड्रोजन बॉन्ड फॉर्मेशन करेगा, ये ऑक्सीजन भी हाइड्रोजन बॉन्ड फॉर्मेशन करेगा, राइट. सो दिस इज द थिंग बाय विच इट इज गोइंग टू कनेक्ट. तो मैं ये कह सकता हूं कि यहाँ पे जो है एक और मॉलिक्यूल से जुड़ा होगा, यहाँ पे एक और मॉलिक्यूल से जुड़ा होगा और यहाँ पे एक और मॉलिक्यूल से जुड़ा होगा. आई कैन से लाइक दैट. Now we'll go and find out what are the questions they are asking. So the number of hydrogen bonds formed by one boric acid molecule. सो द वैल्यू ऑफ x वी नो, x की वैल्यू कितनी आ रही है 6. एक मॉलिक्यूल 6 हाइड्रोजन बॉन्ड बना रहा है, x इज इक्वल टू 6. नंबर ऑफ हाइड्रोजन बॉन्ड्स फॉर्म्ड बाय वन ऑक्सीजन एटम. वन ऑक्सीजन एटम कितने हाइड्रोजन बॉन्ड फॉर्म कर रहा है? केवल एक ही हाइड्रोजन, दो नॉर्मल बॉन्ड है और एक हाइड्रोजन बॉन्ड है. सो y वैल्यू इज इक्वल टू 1. द नंबर ऑफ हाइड्रोजन बॉन्ड्स फॉर्म्ड बाय वन हाइड्रोजन एटम. एक हाइड्रोजन एटम दो बॉन्ड बना रहा है, एक नॉर्मल है और एक हाइड्रोजन बॉन्ड है. सो द वैल्यू ऑफ z इज इक्वल टू 1. सो द सम ऑफ दीज 3 is equal to 8. So 8 will be the answer. ये इसका स्ट्रक्चर है, इस स्ट्रक्चर से भी बना लेंगे, लेकिन वहां एग्जाम में तो ये स्ट्रक्चर होगा नहीं, तो दिस फॉर्म इज मोर इजी टू रिमेम्बर एंड सॉल्व इट. नेक्स्ट क्वेश्चन, फाइंड द वैल्यू ऑफ a plus b plus c plus d in a regular B12 icosahedron. सो आइकोसाहेड्रन में स्ट्रक्चर बनाना आसान नहीं है, बट व्हाट आई रिमेम्बर दैट आइकोसा का मतलब होता है 20. तो इसके पास 20 ट्रायंगुलर फेसेस हैं. जैसे टेट्राहेड्रन में ट्रायंगुलर फेसेस 4 हैं एंड ऑक्टाहेड्रन में 8 हैं, वैसे ही आइकोसाहेड्रन में 20 ट्रायंगुलर फेसेस हैं. 12 बोरोन एटम्स हैं. एक बोरोन एटम 5 बोरोन एटम से अटैच्ड है. नाउ विल मूव एंड सॉल्व द क्वेश्चन, राइट. सो फर्स्ट इज how many boron atoms are equidistant from a given boron atom? So that is equal to 5. एक बोरोन एटम 5 बोरोन एटम से अटैच्ड है और वो नॉर्मल बॉन्ड्स नहीं है, दे आर 3 सेंटर 2 इलेक्ट्रॉन बॉन्ड, बिकॉज नॉर्मल बॉन्ड तो केवल 2-3 ही हो सकते हैं, बोरोन की वैलेंसी 3 है. The second is how many edges are there? This can also be logically find out. If I am finding B, मुझे पता है कि एक बोरोन एटम कितने बोरोन एटम से कंबाइन हो रहा है, 5 से. लेकिन if we are counting the number of edges, I can show here that one boron atom is attached with 5 boron atoms. लेकिन ये जो मैं काउंट कर रहा हूँ, 12 बोरोन एटम से मैंने 12 को 5 से मल्टीप्लाई कर दिया, दैट विल बी 60, बट आई हैव काउंटेड द सेम थिंग ट्वाइस. इस बोरोन एटम के लिए भी ये बॉन्ड मैंने काउंट कर लिया है ना. तो अगर मैं यहाँ पे लिखता हूँ कि व्हाट शुड बी देयर, तो एक बोरोन एटम 5 बोरोन एटम से अटैच्ड है, बट एक बॉन्ड 2 में शेयर हो रहा है. सो इफ आई सिंप्लीफाई दिस, दिस इज इक्वल टू 30. तो A की वैल्यू 5 है, B की वैल्यू 30 है, C क्या है, हाउ मेनी टोटल्स वैलेंस इलेक्ट्रॉन्स आर देयर. एक बोरोन के पास 3 इलेक्ट्रॉन है, टोटल 12 बोरोन एटम्स हैं, तो 36 C की वैल्यू होगी. D ऑप्शन इज हाउ मेनी इक्विलेटरल ट्रायंगल फेसेस आर देयर इन वन B12 यूनिट. नाम ही इसका पड़ा है आइकोसा, आइकोसा ग्रीक में 20, राइट. और अगर आपको समझाया जाए तो इस स्ट्रक्चर में 5 ऊपर है, 5 नीचे हैं, और यहाँ इस रेंज में 10 है, इसमें 10 है. ये जो 5 एटम्स हैं वो हर एक एक ट्रायंगल इधर गिन लो, और ये वाले 5 एक एक ट्रायंगल इधर गिन लो, राइट. सो इफ यू काउंट लाइक दैट यू विल गेट दैट 10 हियर एंड दिस इज 5 एंड दिस इज 5. नाम ही इसका है आइकोसा, आइकोसा का ग्रीक मतलब होता है 20. तो अब इन सबको जोड़ देते हैं. इफ आई हैव टू फाइंड आउट a प्लस b प्लस c प्लस d, ये हो गया 50, 86, 86 and 5 is 91. So answer should be 91. 91 आंसर हो गया इसका. Next question, find the pH of a solution obtained by adding 1 mole of colemanite in 1 liter of water given K of boric acid, right. तो अब मैं इसको लॉजिकली समझाता हूं, राइट. कैसे हमें इसका स्ट्रक्चर याद रखना है कि 4 पॉजिटिव चार्ज आ गए, Ca2, बोरोन एटम्स 6 हैं, BOB बॉन्ड कितने होंगे, 8 होंगे. हर बोरोन एटम से कितने OH ग्रुप अटैच है, एक, तो 6 OH ग्रुप अटैच्ड हैं. फ्रॉम हियर इफ यू सिंप्लीफाई यू विल गेट दैट 6 हाइड्रोजन यहाँ हो गए, टोटल 10 हैं, तो 2 वाटर ऑफ क्रिस्टलाइजेशन हो गए. तो ये एक्चुअल स्ट्रक्चर है इसका. नाउ इफ आई ऐड इनटू वाटर, what is going to happen? First it will dissolve in water to form 2 times of calcium 2 plus iron plus ये जो भी anion है, I'm not drawing the structure but this anion is there, right. We know the structure of this anion. Then what will happen that this anion is going to react with water and the number of BOB bonds is equal to 8. BOB जो bonds होंगे वो 8 होंगे. So 8 water of crystallization यहाँ use होगा. एंड बिकॉज ऑफ दैट 4 बोरोन एटम्स नेगेटिवली चार्ज हैं, तो वो किस में कन्वर्ट हो जाएंगे, BOH4 टेट्राहेड्रल यूनिट में कन्वर्ट हो जाएंगे. और 2 बोरोन एटम्स के ऊपर कोई चार्ज नहीं है, वो ट्रायंगुलर यूनिट्स में कन्वर्ट होंगे, 2 मॉलिक्यूल्स ऑफ बोरिक एसिड, दिस विल गोइंग टू हैपन. So now I can write that pH is equal to pKa plus log, it is a buffer solution, so concentration of base that is equal to 4 and concentration of acid that is equal to 2. रेशियो लिख रहा हूं तो ये log 2 हो गया. pKa की वैल्यू दे रखी है, pKa की वैल्यू बोरिक एसिड के लिए होगी 10 minus log 8 plus log 2. So if I simplify this, I can write that this value is equal to 10 minus log 2 की वैल्यू 0.3 है, so 3 times of 0.3 और यहाँ पे ये 0.3 होगा. So we can simplify this because 8 is 2 to the power 3, so 3 log 2 is 3 into 0.3. So if I am simplifying, I am getting that this value is 10 minus 2 times of 0.3. So that is equal to 10 minus 0.6. 10 minus 0.6 is equal to 10 minus 0.6 आ रहा है 9.4. एक बार चेक कर लेते हैं. 9.4 will be the answer. मैं ये आशा करता हूँ कि ये वीडियो आपके लिए यूजफुल होगा. थैंक यू वेरी मच.